this is my report. The life cycle for development. We describe above the present, the process of design, in somewhat pipeline order. Software engineering is the discipline for understanding the software design from process of life cycle. The software life cycle are requirement, expectation, architectural design, detailed design, implementation and unit testing, integration and testing, operation, and maintenance. Requirements specification concentrates on what the system is supposed to do. In requirements specification, the designer and customer try to capture a description of what the eventual system will be expected to provide. This is the contrast determining how the system will provide the expected service. Architectural design provides a decomposition of what the system description that allows for isolated development. As I mentioned, the requirement specification concentrate on what the system is supposed to do. The next is concentrate on how the system provides the service expected from it. It is not only concerned with the functional decomposition of the system, determining which components provide which service. It must also describe the interdependencies between separate components and the sharing of resources that will arise between components. Detailed design is for a component of the system should be in such a form that is possible to implement in some executable programming language. The detailed design is a refinement of the component description provided by the architectural design. The behavior implied by the higher level description must be preserved in the more detailed description. Typically, there will be more than one possible refinement of architectural component that will satisfy the behavioral constraints. Implementation and unit testing. The component can be tested to verify that it will be performed correctly according to some test criteria that were determined in earlier activities. The goal of this unit testing is to isolate each component of a product, system, or program and show the performance of this individual component is correct. Integration and unit testing. Possible at this time to perform some acceptance testing with the customer to ensure that the system meets their requirement. It is only after acceptance of the integrated system that the product is finally released to the customer. Once enough components have been implemented and individually tested, they must be integrated as described in the architectural design. Further testing is done to ensure correct behavior and acceptable use of any shared resources. It is also possible at this time to perform some acceptance testing with the customer to ensure that the system meets their requirements. Operation and maintenance. That is provide feedback to all of the other activities in the life cycle. After product release, all work of the system considered under the category of maintenance until such time as a new version of product demand a total redesign or the product is phased out entirely. Consequently, the majority of the lifetime of a product is spent in the maintenance activity. Maintenance involved the correction of errors in the system which is discovered after release and the revision of the system services to satisfy requirements that were not realized during previous development. Final point about the traditional software life cycle is that it does not promote the use of notation and techniques that support the user's perspective of the interactive system.
This is my report. Usability engineering. One approach to user-centered design has been the introduction of implicit usability engineering goal into the design process as suggested by Whiteside and colleagues at IBM and Digital Equipment Corporation and by Nelson at Bellcore. Engineering depends on interpretation against a shared background of meaning, agree goal, and understand of how satisfaction completion will be judged. Emphasis for usability engineering is in knowing exactly which criteria will be used to judge a product for its usability. What is usability engineering? Usability engineering is a professional discipline that focuses on improving the usability of interactive systems. It's drawn theories from computer science and psychology to define problems that occur during the use of such a system. Usability engineering involves the testing of design at various stages of the development process with user or with usability expert. In relation to the software life cycle, one of the important figures of usability engineering is the inclusion of usability specification forming part of requirements specification that concentrate on figures of the user-system interaction, which contribute to usability of the product. Various attributes of the system are suggested as gauge for testing the usability. For each attribute, six items are defined to form the usability specification of that attribute. Sample usability specification for undo with a VCR. All attributes. Measuring concept. Measuring method. Now level. Worst case. Plan level and best case. Measuring concept. Undo an erroneous programming sequence. Measuring concept is the process by which we describe and ascribe meaning to the key fact, concept, or the other phonema that we are investigating. Measuring method. Number of explicit user action to undo current program. Measuring method. Usability is generally measured using a number of observable and quantifiable metrics that overcome the need to rely on simple intuition, since there are several quantitative data sources that one can measure. Now level. No current product allow such an undo. The now level describes the current state of the system. How the current state system pair against the measurement. The worst case plant level and best case describes what the designer should aim for in their design. Worst case. As many action as it takes to program in mistake. Worst case. The worst case, planned level and best case describes what the designer should aim for their design. Planned level. A maximum of two complex user actions. Planned level. A planned label is a set of attributes that identify and label key figure value and form parts of definition of planning area. The attributes you have assigned to the planning area are available from planning level, as well as the time profile level, and the attributes assigned to the time profile level. Best case, one explicit cancel action. Best case is the function which performs the minimum number of step on input data of n elements.
Iterative design and prototyping. The only way to be sure about some features of the potential design is to build them and test them out on real users. The real design can be modified to correct any false assumptions that were revealed in the testing. So, iterative design and prototyping is a repeating cycle of designing, prototyping, testing, and refining multiple versions or iterations of a product. It differs from traditional design in that it's more collaborative and you can refine the design as you go. Iterative design is a design methodology based on a cyclic process of prototyping, testing, analyzing, and refining a product or process. Based on the results of the testing, the most recent iteration of the design changes and refinements are made. There are three main approaches to prototyping: the throwaway, incremental, and evolutionary. Throwaway. The prototype is built and tested. The design knowledge gained from this exercise is used to build the final product, but the actual prototype is discarded. So in throwaway prototyping, it means that building initial ideas for different applications, interfaces, or functions without necessarily having the intention of including them in the finished system. Rather, the idea is to gather feedback, prove concept, or undertake other research tasks. Incremental. The final product is built as separate components, one at a time. There is one overall design for the final system, but it is partitioned into independent and smaller components. In incremental prototyping, separate small prototypes are built in parallel. The individual prototypes are evaluated and refined separately, and then merged into a comprehensive whole, which can be evaluated for consistency in look, feel, behavior, and terminology. Evolutionary. Here, the prototype is not discarded and serves as the basis for the next iteration of design. In this case, the actual system is seen as evolving from a different limited initial version to its final release. In other words, evolutionary prototyping is a software development method where the developer or development team first construct a prototype. After receiving initial feedback from the customer, subsequent prototypes are produced, each with additional functionality or improvements until the final product emerges. Techniques for prototyping. Storyboards. The simplest notion of a prototype, which is a graphical depiction of the outward appearance of the intended system without any accompanying system functionality. So, a storyboard is a narrative prototype usually created in the early stages of the software making process to articulate business and marketing requirements in the form of a usage scenario or story. Limited functionality simulations. More functionality must be built in the prototype to demonstrate the work that the application will accomplish. Storyboard and animation techniques are not sufficient for this purpose, as they cannot portray adequately the interactive aspect of the system. To do this, some portion of the functionality must be simulated by the design team.
Decision rationale. Decision rationale is the explicit listing of decisions made during a design process and the reasons why those decisions were made. And the next is decision rationale techniques. Process oriented preserves order of deliberation or decision making, hierarchical or tree-like. Root issue positions are potential resolutions of an issue and are descendants supported or refute by arguments, add secondary issues, or etc. Issue-based information system or tinatawag natin na IBIS. Graphical in nature. So the next is design space analysis. Structure-oriented emphasize post HOC structuring of considered design alternatives, questions, options, and criteria. QOC hierarchical structure questions and represent major issues or of a design. So, itong process-oriented design is interested in recording an historically accurate description of a design team making some decision on a particular issue for the design. In this sense, process-oriented design rational becomes an activity concurrent and the rest of the design process, and the issue-based information system or sa tawag natin nga na IBIS is an argumentation-based approach to clarifying weak problems, complex ill-defined problems that involve multiple stakeholders. And the next is design space. Design space analysis is an approach to representing design rational. It is a semi-formal notation called QOC or tatawag natin na questions, options, and criteria to represent the design space around an artifact. So next is, and the last is physiological design. Rational proceeds by having the designers of the system record what they believe are the tasks that the system should support and then building the system to support the task. The designers suggest scenarios for the task which will be used to observe new users of the system.
Principles support usability. The most abstract design rules are general principles, which can be applied to the design of an interactive system in order to promote its usability. The principles we present are divided into three main categories: learnability, flexibility, and robustness. The principles we present are first divided into three main categories. Learnability, the ease with which new users can begin effective interaction and achieve maximal performance. Flexibility, the multiplicity of ways in which the user and system exchange information. Robustness, the level of support provided to the user in determining successful achievement and assessment of goals. Summary of principles affecting learnability. Predictability. Predictability of an interactive system means that the user's knowledge of the interaction's history is sufficient to determine the result of his future interaction with it. This interactive design principle requires a user's knowledge of interaction to be sufficient to determine the outcome of present or future interaction with the system. Synthesizability, support for the user to assess the effect of a past operation on the current state. In general, this principle relates to the ability of the interactive system to provide the user with an observable and informative notification about the operation state changes within the system. Familiarity. For a new user, the familiarity of an interactive system measures the correlation between the user's existing knowledge and the knowledge required for effective interaction. The familiarity principle is concerned with the ability of an interactive system to allow a user map to prior experiences, either real-world or gained from the interaction with other system, onto the future of a new system. Generalizability. The generalizability of an interactive system supports this activity, leading to a more complete predictive model of the system for the user. This interactive design principle provides support for users to extend knowledge of specific interaction within and across application to new but similar situations. Consistency. Consistency relates to the likeness in behavior arising from similar situation or similar task objectives. Consistency is probably the most widely mentioned principle in the literature on user interface design. Consistency is essential and is probably one of the most widely applied design principles in user interface design. Consistency between applications is always favorable, however, consistency within an application is essential. Summary of principles affecting flexibility. Dialogue initiative. It is important to consider which partner has the initiative in the conversation. The system can initiate all dialogue, in which case the user simply responds to requests for information. When the system controls the dialogue flow, the dialogue is said to be system preemptive. Conversely, when the flow is controlled by the user, the dialogue is said to be user preemptive. In general, a user preemptive dialogue is favored, although some situations require a system preemptive dialogue. In reality, some line between these two extremes is usually the most satisfactory solution. Multithreading. Multithreading of the user system dialogue allows for interaction to support more than one task at a time. Multithreading within an interface provides support for multiple tasks to be performed at one time. Multithreading can be described as concurrent or interleaved. Task migratability. Task migratability concerns the transfer of control for execution of tasks between system and user. Task migratability means passing responsibility of execution tasks between user and system. A computerized spell checker is a good example to this. It is a waste of time for a user to manually check a very long document and correct. A spell checking facility in a word processing application can check word against its own computerized dictionary. Substitutivity. Substitutivity requires that equivalent values can be substituted for each other. For example, in considering the form of an input expression to determine the margin for a letter, you may want to enter the value in either inches or centimeters. Customizability. Customizability is the modifiability of the user interface by the user or the system. The customizability principle supports a user's ability to adjust system settings or features to a form that best suits the preferred way of usage. Standards. Standards for interactive system design are usually set by national or international bodies to ensure compliance with a set of design rules by a large community. Standard is an obligatory design requirement for any project. These standards are not advisory, they must be followed, just like the requirements in the building code, fire code, or electrical code. Characteristic between hardware and software, which affect the utility of design standards applied to them. Underlying theory. Standards for hardware are based on an understanding of physiology or ergonomics, human factors, the results of which are relatively well known, fixed and readily adaptable to design of the hardware. Change. Hardware is more difficult and expensive to change than software, which is usually designed to be very flexible. Consequently, requirements changes for hardware do not occur as frequently as for software. Since standards are also relatively stable, they are more suitable for hardware than software. Usability. The effectiveness, efficiency, and satisfaction with which specified users achieve specified goals in particular environments. Effectiveness. The accuracy and completeness with which specified users can achieve specified goals in particular environments. Efficiency. The resources expended in relation to the accuracy and completeness of goals achieved. Satisfaction. The comfort and acceptability of the work system to its user and other people affected by its use. Guidelines. We have observed that the incompleteness of theories underlying the design of interactive software makes it difficult to produce authoritative and specific standards. As a result, the majority of design rules for interactive systems are suggestive and more general guidelines. Guidelines are sets of recommendations on how to apply design principles to provide a positive user experience. Designers use such guidelines to judge how to adapt principles such as intuitiveness, learnability, efficiency, and consistency so they can create compelling designs and meet and exceed users' needs.